Hey, welcome. So, have you ever stopped to think if there are problems that a computer just can't solve? And I don't mean because it's not powerful enough. I mean problems that are fundamentally, logically impossible to ever get an answer for. Well, today we're going to dive right into that, exploring the absolute outer limits of what computation can even do.
It all kicks off with this one, kind of simple sounding question. Could you build a master program, a sort of universal bug checker, that could look at any other code you give it and say with total certainty, yep, that one will finish, or nope, that one's going to get stuck in an infinite loop? This is the famous halting problem. And honestly, it's the key that unlocks this whole conversation.
To get why this is so tricky, just imagine for a second that we did have that perfect predictor program. Now, let's build another kind of mischievous program. And what it does is it takes the predictor's answer and does the exact opposite. So if the predictor says a program will halt, our machine deliberately loops forever. If the predictor says it'll loop, our machine just halts immediately. Okay, so what happens when we ask the predictor to analyze our mischievous program? Well, it creates this head-spinning paradox, right? Which kind of hints that our perfect predictor couldn't have existed in the first place. Now, to really prove this kind of stuff, we can't just talk vaguely about programs. We need a universal standard, a theoretical computer that can handle any possible algorithm. And for that, we have to thank the genius Alan Turing. The Turing machine is basically the ultimate idealized computer. It's a really simple idea, actually. You've got this infinitely long tape, a little head that can read, write, and move, and a set of instructions. But here's the crucial part. That simple model is powerful enough to simulate any algorithm you could ever run on any computer. It's our universal measuring stick for what is and is not computable. So when you feed an input to a Turing machine, it can only ever do one of three things, just like any program on your laptop. First, it could run for a bit, stop, and say, yes, I accept this input. Second, it could run, stop, and say, no, I reject this input. Or third, it could just get stuck, running forever and ever, never giving you an answer. These three outcomes, they're the foundation for everything we're about to talk about. Okay, so using those three possible outcomes, we can start sorting every computational problem you can imagine into two really important boxes. And this is where we finally get to the heart of our question. What exactly is a recursive language? So, the first box is for what we call recursively enumerable languages. You can also think of them as recognizable. For any problem in this class, you are guaranteed to get a yes answer if it's a valid input. The machine will stop and accept it. But, and this is a big but, for an input that should be a no, the machine might stop and reject it, or it might just loop forever. You're not guaranteed a clear no. It's more like yes or maybe. And that brings us to the second, much more powerful category, a recursive language. Here's the absolute game-changing difference. A Turing machine for a recursive language is guaranteed to stop on every single input. It will always give you a final answer, either a clear yes or a clear no. It never leaves you hanging. Let's just put them side by side to make it super clear. Recursively enumerable gives you a guaranteed yes, but for the no cases, you might be left waiting forever. Recursive, on the other hand, guarantees an answer, period. And that last row there, that's the real payoff. The special word for a problem that fits in the recursive language class is decidable. You see that guarantee of halting, the fact that you always get an answer? That is the single most important idea here. It's literally what we mean when we say a problem is truly, fundamentally solvable with an algorithm. And our source material here puts it about as perfectly as you can. A problem is said to be decidable if there exists some algorithm which solves the problem. That's it. That's the gold standard. So here's the bottom line, the direct connection we've been building up to. A problem is decidable if and only if it can be described by a recursive language. Why? Because that's the only class of problems where you are absolutely 100% guaranteed to get a final answer for every single question you could possibly ask it. All right, let's bring it all home. Now we can take everything we've just learned about Turing machines and these different language classes to finally crack the mystery we started with. So let's ask our original question again, but this time using our new, more precise language. Is the halting problem a recursive language? In other words, is there a Turing machine that can take any program and its input and be guaranteed to stop and give us a yes it halts or no it doesn't answer? And the answer, proven by that paradox we looked at in the beginning, is a huge no. It's impossible. No algorithm, no Turing machine can exist that solves the halting problem for every single case, so it is not a recursive language. It is recursively enumerable because we can find out if something halts by just running it and seeing if it stops. But since we can never be sure about the ones that loop forever, it is fundamentally undecidable.
I mean, that is a pretty mind-bending thing to wrap your head around. Our inability to solve the halting problem isn't because our computers aren't fast enough or we haven't written clever enough code. It is a fundamental mathematical limit on what algorithms are capable of doing ever. Some questions are just provably, eternally unsolvable.
So the huge takeaway here is that computation itself has hard limits, and they're defined by these classes of problems. The halting problem is just the most well-known example. And it leaves you with this really fascinating question to ponder. What other problems that seem simple on the surface, things like proving a program is 100% bug-free, might also be lying just beyond that boundary of what is even decidable?